Welcome back to this next video in which we are discussing bases of vector spaces. Okay, so in the previous video then we saw what the definition of a basis of a vector space is. Okay, we saw that a basis is a set of vectors from the vector space such that the span of this set of vectors is equal to the entire vector space. Okay, so you can get any vector in the vector space by taking a linear combination of the basis vectors. Okay, in addition, the second property that it needs to have is that it's linearly independent. Okay, so the vector, this set of vectors that is the basis, needs to be linearly independent. And remember, what that means is that there can be only one linear combination of the vectors in this set which actually gives the zero vector. And the only linear combination that does that must be the linear combination where all of the scalar coefficients in front of the n vectors are zero within the field. Okay, so the additive identity of the field. Okay, and we know that what that then gives rise to is the fact that all the different linear combinations of the vectors in that set of linearly independent vectors must actually give different vectors within the vector space. Okay, so no two distinct linear combinations of the vectors from this set can give the same vector in the vector space. So what this overall means is that every vector in the vector space can be written as a linear combination of the basis vectors in one and only one way. Okay, so this means that for any vector, little v, I can write it out like so as a linear combination of my basis vectors, and there's only one way you can do that. Okay, so if I set two people off to find a linear combination of the basis vectors which gives you this vector, they both come back with the same answer, always. There's only one answer. Okay, and this then means that we can describe all elements of the vector space in terms of these coefficients that you have to put in front of the n vectors of the basis, and these coefficients are called the coordinates of that vector with respect to the basis capital B, and what we can do is arrange them nicely in a column like so, and we'll call this the coordinate vector of this vector. Okay, so this is why bases are so useful, because it allows us to describe all of the other vectors in the vector space in terms of the coordinates with respect to the basis. Okay, and we saw how nice coordinate vectors are. We saw that if we want to add two vectors together, the way the coordinate vectors change, okay, so the coordinate vector of the two vectors added together is just all of the components added together, basically. Okay, so all of the coordinates just add, so the different scalar coefficients in front of the different basis vectors just add together. Okay, so that's beautiful. And in addition, scalar multiplication of a vector, again, all you do is multiply all of the coordinates by that scalar, and that's how the coordinate vector will end up changing. So this is why coordinate vectors are so beautiful, and coordinate vectors is what we're trying to seek with producing bases of vector spaces. Okay, now, what I want to stress is that you can have lots of different bases of a vector space. There is not just one basis of a vector space. You can form absolutely loads of them. It's just a set of vectors which spans the entire vector space and which is linearly independent. It's not the case that there is just one of these. Okay, now, all bases of a vector space are going to have the same number of elements in. Okay, now we're not going to prove that in this video. We're going to leave that till the next video, which will be entitled Dimension of Vector Spaces. Okay, and in that video what we'll do is prove this point that different bases will have the same number of vectors in. Okay, right, what I want to finish up with in this video is just give you a few examples of bases of vector spaces. Okay, so firstly what I want to do then is tackle a problem that pops up occasionally. Okay, and this is, what is the basis of the zero vector space? Okay, so let me just remind you of what the zero vector space is. Okay, so the zero vector space is a bit of a trivial vector space. This is a vector space that contains only one element. Okay, and that one element is going to be the additive identity of the vector space. Okay, so we might as well call it 0, although you could use whatever symbol you like. Okay, so here is our zero vector space, and as a set it's just going to contain one element, and we'll give that element the symbol 0, but as I say, you could use whatever symbol you like for it. Okay, now the addition law then on this vector space is going to be very trivial. Okay, we're only going to have one possible addition, so here's our addition composition table, 0 plus 0. Okay, well if this is going to be closed, the only answer can be 0. Okay, so there's our addition composition law. Now, I didn't tell you what field this was going to be over, and in fact it can be over any field you like, so 0 vector space over an arbitrary field f. Okay, so now let's have a look at the scalar multiplication law. So let's put our scalar multiplication law here, so we'll have multiply here. Okay, and we'll put all of the elements of the field down here, and this field could potentially be incredibly complicated. It could be the real numbers. It could be a huge, uncountably infinite set of symbols. Okay, but we'll put them all down here. We'll give them all a row, and then the only actual vector that we're going to have up here is the 0 vector, because that's the only vector in this vector space. Okay, and of course we know that the additive identity of a vector space must multiply by all elements of the field to give back the additive identity if it's going to obey the axioms of a vector space. Okay, so you just have to have 0, 0, 0 as all your answers here. In fact, it can't be anything else because scalar multiplication has to be closed. Okay, and idiotically, this does actually obey the axioms of a vector space. Okay, so this has to be counted as a vector space, even though it's so stupid, and it's called the 0 vector space over the field f. And as I say, you can use whichever field you like here. They're all vector spaces. Okay, now here's the problem. Try and find me a basis for this 0 vector space, and you will hit problems. Okay, so this isn't particularly difficult. Okay, let's try and construct a basis here. Okay, well, we'll construct a set of vectors from here. Well, there's only one vector that we can use, so we might as well just stick that in. So here is our hopeful basis. But is this a basis? Okay, well, it satisfies the first condition. It does indeed span the entire vector space. If I take every linear combination of this vector here, I will indeed get the entire vector space back again. So I will take the 0 vector, multiply it by all elements of the field, I'll get lots of copies of the 0 vector, okay, and that will obviously generate me the entire vector space back again. The problem is it fails criterion number 2. The criterion that it is linearly independent, which says that there must be only one linear combination of the basis vectors which gives you the 0 vector. Of course, you can multiply this by any element of the field, okay, and get the 0 vector. So there's loads of linear combinations of the basis vectors in this set, which gives you the 0 vector. Okay, which all give you the 0 vector. So this fails linear independence. So this is not a basis of the 0 vector space. Okay, so what is a basis of the 0 vector space? Well, here comes an unintuitive definition, but a definition that we will see in the next video when we discuss dimension, and when we try and do a few of the proofs in that will be useful. Okay, we are going to define the basis of the 0 vector space to be the empty set, the set that contains nothing. Now, I agree that that is an unintuitive definition. How does that span the entire vector space? What exactly am I taking linear combinations of? Okay, however, we are going to just make that definition that the basis of the 0 vector space is the empty set, and that this empty set is going to span the 0 vector space. Okay, we're just going to state that as fact. We're going to define that. Okay, and you might think, well, what a stupid definition, but there is logic behind it. It makes certain proofs work. Okay, so at the moment, this is just going to look like an unmotivated, stupid definition that you're just going to have to memorize, but you will see why this is important in the next video when we have certain proofs, and if this wasn't the case, the proof would be messy, basically. You'd have to have, okay, case 1 this and case 2 this, whereas if this is true, if we make this definition, it'll make the proofs more elegant. Okay, so that is the definition that people usually use for the basis of the 0 vector space. But I agree, at the moment you're probably thinking how stupid, but there is logic behind it. Okay, right, so that's the first thing that I want to say. Now on to something more sensible. Let's have a look at an example of a basis of a vector space. Okay, and the vector space that I'm going to show you is our old favourite Fn. Okay, so you might have thought I was about to do R3, but we'll go more general. We'll go to an arbitrary field N. I'll firstly just remind you of what this vector space actually is, Fn, where F is some arbitrary field, and then we'll have a look at a basis for this. Okay, we'll have a look at a very special basis for this, or rather a not so special basis that is given a title really that it doesn't deserve, and that's one of the key lessons that I want to try and convince you of in this video, and which I hope to continue on in the previous videos. And one of the key concepts, it's not a deep result, but it is a really key concept that people find difficult to understand. Okay, so looking at this will illustrate this key concept. Okay, so let me firstly just remind you of what Fn is as a vector space. So this is a vector space over an abstract field F. Okay, so this field could be the real numbers, it could be the rationals, it could be the complex numbers, it could be one of our beautiful prime fields, or if you know them, the other finite fields. If you don't, we haven't seen them yet. Don't worry about them. Okay, but it is a vector space over some abstract field F. Okay, and the way that we actually construct this thing is we take all n tuples of elements of the field. Now we can either arrange these as row vectors or column vectors. I keep flipping between the two. At the moment it doesn't matter because we haven't defined them to have anything different apart from one another. They're just different symbols. Okay, so we'll go for column vectors today. Okay, so we'll have x1, x2, all the way down to xn. Okay, so here is a column vector, and all of the entries in this column vector are going to be elements of the field. So xi's are all elements of the field, capital F here. Okay, so this is going to be the set that is going to form the vector space. So at the moment this is just the set. I need to show you the addition law and the scalar multiplication law to actually turn this into a vector space. So here's the set, and I hope this is a intuitive set. So what you're doing is you're taking every possible n tuple of elements of the field. So x1 varies over all elements of the field, x2 varies over all elements of the field, all the way down to xn varying over all elements of the field. Okay, you put all of these into a great big set, every possible combination that you can possibly construct, stick them all into a set, and that's the set that we're going to turn into a vector space. Okay, so then what we do is we define an addition law on this. Okay, so if I've got two vectors, x1, x2, all the way down to xn here, and I want to add it to another vector, and I'll call this the bar 1, x bar 1, x bar 2, all the way down to x bar n, how am I going to define that? Well, the way I'm going to define it is that you're going to add the components in the field. So you'll add x1 to x1 bar, where this plus sign here, this now means plus in the field. Okay, so these are elements of the field, capital F here. Okay, in a field you can add two elements together. For instance, in the real numbers you can add two numbers together. Okay, so you'll add these two elements together in the field. The same for the second component, so you'll add x2 to x2 bar, and you'll go all the way down and you'll add xn to xn bar in the field. So you add all the components together in the field, like so. So that's how we define addition in on this set, okay? And we check in the video on definition of a vector space earlier on in this playlist on vector spaces that this addition law on this set actually does obey the axioms that it needs to obey. Specifically, it obeys the axioms of an abelian group. Okay, so addition is fine. Then, to define scalar multiplication, let's say we've got some element of the field, little c here, and we want to multiply it by this vector x1, x2, all the way down to xn here. Well, the way we're going to define the element of the field multiplied by this vector is we'll do it component-wise. So we'll just multiply all the components by c, this element of the field, in the field. So all of these multiplications here this multiplication, this multiplication, this multiplication, etc. These are all multiplications in the field, okay? So again, well defined because the field has a multiplication law on it. Again, think of the real numbers. Okay, so this is how I will define scalar multiplication, and again in that video on definition of a vector space we actually do the checks to make sure that with this definition of scalar multiplication this set does actually satisfy the axioms of a vector space. Okay, so that's a reminder of how this vector space works. Now let's talk about bases of this vector space. So the first basis that I want to talk about is the basis that everyone thinks of as the only basis, but it is not the only basis. Again, this is the key concept that I want to talk about, how this basis that I'm about to show you is not actually that important at all. Okay, so of a vector space of this form, Fn, there is what's known as the standard basis of a vector space Fn. Okay, but this is a misnomer. Okay, this gives it more importance than it actually has. Okay, however, this is what it's called. Right, so let me tell you then about the standard basis. So firstly, the standard basis, the first injustice that is given to this standard basis is that it isn't denoted by a B, it instead gets denoted by an E. Okay, and it's going to contain n vectors, okay, and these vectors are the vectors of this form here. Okay, so you'll have vectors where you have a 1 in one of the components and 0 in all the other components. So the first one, you'll have 1 in the first component, and then you'll go on and all the other components will have 0. Okay, so you have 1, the multiplicative identity, in the first component, and 0 in all the other components. Then after that, another vector that you'll have in here will be 0 in the first component, 1 in the second component, and then 0 in all the other components right down to the nth component, and you can continue it on. You'll have the one where you have 1 in the third component, 0 in all the other components, 1 in the fourth component, 0 in all the other components, etc., all the way down until you go to the point where you have 1 in the nth component and 0 in all the other components. Okay, so this is a set of vectors. We need to check that it satisfies the two properties of a basis, that it spans the entire vector space and that it is linearly independent. Okay, but firstly, a bit more nomenclature. So these are all given names. Okay, so this one where you have the 1 in position 1 is called E1. This one where you have the 1 in position 2 is called E2, and so on. So when you have it 1 in the position 3, it will be called E3, and then 1 in position n is called En. Okay, now the first thing that I should point out, you might be wondering, well, we were dealing with a general field, so why are you using real numbers here? But remember, 1 and 0 are the symbols that we use for the additive and multiplicative identities in any field. Okay, so 1 just means the multiplicative identity in any field, 0 means the additive identity in any field. So these are symbols that you can use for any field, not just the real numbers or the rational numbers or the complex numbers. They apply in any field. Okay, so let's now check that this set of vectors does actually satisfy the axioms of being a basis. Okay, and then let's shoot it down. Let's say why this is not the only basis. Okay, and why actually it's no more important than any other basis that you can find for this vector space Fn. Okay, so why is it a basis first? So to prove that it's a basis then, we want to prove firstly that the span of this set of vectors is actually equal to the entire vector space Fn. Okay, now this is extremely easy to prove, and this is one of the nice things about the standard basis, is how easy this is to prove. Okay, so we just need to prove that I can get any vector in the vector space Fn by taking a linear combination of these vectors here. Okay, well let's just consider a linear combination of these n vectors here. So a linear combination will look like this: C1 times the first vector here, which is 1 in the first position and then 0s everywhere else, plus C2 times the second vector, which is 1 in the second position and 0s everywhere else, Okay, plus and on it goes all the way down until we have Cn times this nth vector where we have zeros in all the other positions and then 1 in the nth position. Okay, now let's just actually do this. So how do we scalar multiply this vector by C1? Well, of course, we just multiply all of these components by C1. 1 times C1 will give us C1, 0 times C1 will of course give us 0. So this will just end up as C1 in the first component and then 0 everywhere else. Okay, doing the same for the second portion here, we'll end up with C2 in the second component and then 0 everywhere else. Okay, and then on it will go, and then in the nth one over here we'll end up with Cn in the nth position and then 0 everywhere else. Like so, and then when we add all of these together, we'll have C1 plus 0 n minus 1 times from all of these other ones, so we'll end up with C1 in position 1. For position 2, you'll have 0 in all the other ones, and then just C2, and it will go on, and you'll have Cn in the nth position, like so. Okay, and of course C1, C2, Cn could be any elements of the field you liked. Okay, so these could be whatever elements of the field you like. Remember, they were the scalar coefficients in the linear combination here. They can vary over the entire field, so indeed you can make this equal whatever vector in Fn you like. So this set of all linear combinations then of the standard basis vectors does span the entire vector space. Okay, now linearly independent is the second property that we need to prove. Okay, so we need to prove that there is only one linear combination which gives the 0 vector, and that is where all of these scalar coefficients are equal to 0 within the field. Okay, well again we can use this fact here. So we have an arbitrary linear combination of these vectors here. Okay, if we want this to equal 0, the 0 vector, we want all of these components to equal 0. So clearly we're going to need C1 to equal 0, C2 to equal 0, all the way down to Cn equal to 0. That's the only way that you can actually get the 0 vector. So indeed it is linearly independent. Okay, so this standard basis, this set of vectors from Fn, it is a basis of Fn. Okay, now everyone thinks that it is the most natural basis. However, there is nothing particularly that special about it as far as the algebraic structure of the vector space is actually concerned. Okay, you might look at these vectors here and say, aren't they wonderful? Aren't they beautiful? They've got 1 in one component and then 0 in all the other components. They are obviously the perfect basis to use. Okay, but that is not an argument that involves anything to do with the vector space structure. Remember what a vector space actually is. A vector space is a set of symbols with an addition composition and a scalar multiplication composition on. Your arguments as to why these are fantastic basis vectors to use concerns the symbols. Okay, it concerns these symbols that I've used to describe them. Okay, you think that these, in fact, I shouldn't say you, generally people think that these are a fantastic basis to use because of the symbols. The symbols make them look beautiful. But as far as the entire vector space is concerned, there is absolutely nothing special about this basis whatsoever. It is equivalent to all the other bases. It is only special because of the symbols, basically. If I was to relabel up this vector space, if I was to go through Fn and relabel up all of the vectors with silly symbols, so I could relabel this one up as some squiggle like this, I could relabel this one up as phi, I could go on and on relabeling them up in silly symbols, basically. If I did that for all the vectors in here and kept the addition law exactly the same, just changed the symbols around as I've relabeled them, okay, and kept the scalar multiplication exactly the same, just changed the symbols for the vectors, you would not be able to find these anymore. There is nothing special about them as far as the vector space structure is concerned. They are only special because the symbols you have given them make them special. And this is such a key concept to understand, okay, that there is no special basis for a vector space. You can use any basis you like, and they are all utterly equivalent to one another. They are all as good as each other. That is the key concept that I want you to get. Okay, and really, this is at the foundations of so much. Okay, for instance, the theory of quantum mechanics, the concept of different bases and how they are all as good at being bases as each other is at the foundations of quantum mechanics. In quantum mechanics, the state of a particle is described by a vector, albeit an infinite dimensional vector. Okay, and in order to understand different properties of the particle, for instance position and momentum, what you have to do is change the basis which you are using to describe your vector. Okay, so you have to change your coordinate vector for that vector basically by changing the basis that you're looking at the vector with. Okay, in addition, this concept of how bases are utterly equivalent to one another is at the foundations of the mathematics that underlies general relativity. And when people struggle with the mathematics of general relativity, really one of the foundational things that they're missing is this concept that bases are utterly equivalent algebraically. There is no special basis, okay? They are all utterly equivalent. And you might be crying out at the moment, but think of R3. These standard basis vectors in R3 are the perpendicular ones. Okay, so let's tackle that objection. Okay, so we'll have R3 here. Okay, so R3, remember, is just an Fn vector space. Okay, we've made the field now the real numbers, and we've made the n 3 in this case. Okay, so it's the set that contains all triplets of real numbers, x1, x2, x3, where all of these are real numbers. Okay, and the addition laws and scalar multiplication laws are just as we've described for Fn. Okay, right. Now, one of the beautiful ways that we often can get intuition for R3 is that we can ascribe the vectors points in the three-dimensional grid. Okay, and the way that we often do this is we ascribe the vector 1, 0, 0, this point here, okay, which is described by the position vector, which is going like so. Okay, so 1, 0, 0 is usually ascribed this point and this position vector here. So I'll just colour this in. Okay, so here is 1, 0, 0. Okay, usually we ascribe this vector 0, 1, 0, E2 if you like. In fact, I'll use this nomenclature, so we'll call that one E1. Okay, we'll call this silly one here E2. Okay, and usually that one's ascribed this one, which points perpendicular to that one. Okay, so I'll colour this one in turquoise here. And then finally, the final standard one, which is 0, 0, 1, E3, is usually then given this point that's 1 up here, okay, and is pointing in the final direction, like so. Okay, so your objection might be that these three are completely natural because they're the ones that are perpendicular to each other and of length 1. Okay, but I defined that map. I said I wanted these to be ascribed those vectors. Again, it was completely man-made that I did ascribe those three vectors, those three position vectors in terms of this picture. Okay, and the reason I ascribed them those privileged vectors in this picture here is because of how simple their symbols are. So again, it's a lie. You are deceived into thinking that these are incredibly important in this vector space because of their beautiful symbols. I could have ascribed loads of other vectors in R3, these three vectors that I chose to ascribe these vectors to. Okay, and it would have worked exactly the same. What do I mean by that? I mean the addition being so beautifully interpreted in terms of this picture and the scalar multiplication being so beautifully interpreted in terms of this picture. So remember what's beautiful about this picture. The reason we often go to this picture trying to seek intuition is that addition of two vectors in this picture refers to the addition, the putting of the vectors end to end. Okay, so we'll have one vector here and one vector here, and addition can be interpreted as putting this vector here at the end of this one and then joining them up like that. Okay, And scalar multiplication can be interpreted as stretching the vector or flipping it round and then stretching it. Okay, so those beautiful interpretations of the algebraic structure of R3, those still hold if I ascribe different vectors these perpendicular vectors of unit length. Okay, so it was truly arbitrary that I chose to ascribe this one to this position vector in green here, this one to this position vector in turquoise, and this one to this position vector in purple. Okay, you can do it different ways, and we will explore this concept more in other videos. Okay, so what I'm trying to say here then is that this standard basis is only special. It only holds a privileged position in the vector space Fn because the symbols are nice for these ones. Okay, these are not algebraically important at all. If you were to relabel them up, then you would not be able to find them. There is no algebraically distinguishing properties about them. They are special only because their symbols are special. Again, that's a really, really important key concept. Okay, so I think we will call it there for this video.